real sensors with real data and from a real environment and real conditions need to be mirrored almost identically in this virtual environment where you're running the simulation. Otherwise, the algorithms and that decision of who wins, the LiDAR or the radar, isn't going to be able to be as effective and safe. Hey guys, welcome to Embedded Toolbox, the video interview series where we try to save the world by solving one engineering challenge at a time. And today, one of the engineering challenges we're trying to solve is the evolution of autonomous drive and all of the tools and all of the intelligence and all of everything else that's needed in order to make that a reality. And to help us navigate this new roadway, we brought on Michael Pepperova, who is the lead product manager for simulation modeling and scenarios at DSpace. How you doing, Michael?
Yeah, hi, Brandon. Thanks, I'm fine.
Very good. So there are so many elements of an autonomous vehicle and an autonomous drive platform that makes your head hurt. That's one of the reasons that today so many people are interested in advancing the art around modeling, simulation, and visualization when it comes to AV engineering. So what are the big ways in which that core group of technologies, and it's hard to really separate them from one another today, what are the ways in which that's changing from how we've done things in the past for automotive?
Okay. The topic of simulation is not new. So everybody wanted, starting 20 years ago already, when everybody wanted to validate their electronic stability control, steering control in the lab. But what comes now in, and it's getting more and more challenging, is a big part of AI. Where is this needed? In the AV stack, the perception layer has to do his decision on his own. And the first challenging part is to detect all of the different elements out there completely on their own. The radar, the camera, the LiDAR system. And then bringing all of these three different elements together at the so-called sensor fusion layer. What about if the camera says this and the radar says this? Who win?
Right.
Yeah, so this is a big challenge, and therefore you need very maturity sensor level here and perception layer to properly finally feeding in the information into your driving function for braking, steering, powertrain interventions, and so on.
Right. And of course, I think as you're alluding to, the reality is that real sensors need to be mirrored. Real sensors with real data and from a real environment and real conditions need to be mirrored almost identically in this virtual environment where you're running the simulation. Otherwise, the algorithms and that decision of who wins, the LiDAR or the radar, isn't going to be able to be as effective and safe as it needs to be when we're driving these things in the real world, right? So how do you get to this? How do you get to this place where you've got virtual sensors that are acting like real sensors?
Yeah. So first of all, we have a highly automated way to bring in real data into a virtual one. It starts with a pure road geometry, like from HD maps that you may convert to bring it into a virtual environment. And then you have to place a highly realistic 3D environment around it. But just keep in mind, what you as a human see as realistic must not necessarily seems to be realistically for all of the sensor types. Because a radar, a LiDAR, and so on sees the world with different eyes. Yeah. And this is the next big challenge, to have the right material properties put to all of these different elements so that virtual sensors can recognize the virtual environment, but providing realistic feedback into your real perception stack, because that's the one that you would like to validate and develop and so on.
And as we move forward in the levels of autonomy, right, and we now see getting to level 3 and above, you've come out with some new offerings that are really targeted at this type of engineering and this type of development. What can you tell me about Aurelion?
Yeah, Aurelion is our physics-based sensor simulation suite, plus a highly realistic 3D environment. And both working together brings to you the right input to your perception layer of the AV stack. This is what's new there. What was already out there like 15 years ago, we started with the first version of ASM, which is the physics of the car, the physics of the track. And both together makes a union and serves as a basis for the full closed loop validation of your AV stack. Especially for the truck cabin has a very high degree of freedom for pitching when making a full brake. But the real camera is mounted at this cabin. That means during full brake, it will drastically change the field of view. And if you want to take this into account in a simulated environment, you need the physics of the truck cabin and so on. Yeah, so therefore, sometimes it seems to be a little underestimated, the physics of the car, but it only works properly if you have both together, the physics plus the physics-based sensor models.
Great. Do you want to show us a little bit more?
Yes, sure, I can share. I'm logged into our 3D environment, Aurelion. It's the new hot stuff that we brought out. Yeah, so here you can see the truck. Let's rotate around a little bit. Yeah, lights are on, road is there, nice sunset, whatever. All that you need is here. To get a bit better, clearer picture, let me just quickly change the sun a little bit, make it more bright so that you can see all the details later on.
Wow.
Maybe put it here, spinning around. Now here it's a nice looking track. I'm online. Yeah, I'm already in the simulation mode. I just did not tell the driver or the AV stack to start the scenario. I can just press a button. Maybe you can see it's a little bit jumping. Why? It considers the full physics of this track with 1, 2, 3, 4, 5 axles. These 3 axles with twin tire, single tire, steering system. I have everything in here. And here you can see the counter traffic as well. Yeah. Let me quickly reset one because I forgot a very important point. I want to switch on my physics-based sensors.
Okay.
Yeah. So what we have seen so far was the realistic 3D world. But to really stimulate my AV stack, I need to switch on also my physics-based sensors. I have 3 elements in. Yeah.
So these physics-based sensors, I mean, they're modeled after actual sensors, right? I mean, these are sensors that are available from Bosch or Texas Instruments or whomever, correct?
Yes and no, let's say. So typically you have 3 items when talking about physics-based sensors. First of all, you need a highly realistic environment with material properties. Because a LiDAR needs other information from the environment than the radar does, like reflectivity, transparency, and so on. Also different information than the camera needs. Yeah. Then the second one is we have implemented a so-called ray tracer. Ray tracer means, you can see it from here, these are single rays. If this ray hits an element like this reflector post, it goes from here to here to here and back to the source. This is called ray tracer. This is the second item that is very important. And then you need the details of the sensor front module. And here we have 2 approaches. We have a generic one that comes with the installation that you can parameterize, like the scanning pattern for a LiDAR, or you can bring in the IP from the sensor supplier, like from a Velodyne, from a LeddarTech. So we have a large list of sensor suppliers where we collaborate with. I'm not allowed to mention all, but let's see, the LiDAR ones, the new ones. So LeddarTech, Velodyne, Hella for radar, Septon, and many, many more. Yeah.
Very good. And as you mentioned before, there are APIs and you know, it's open enough to be able to bring in a lot of that IP if, you know, depending on who you're using.
Exactly. Perfect.
And
then if you've configured everything, you can start my scenario. This is a logical scenario. And later on, after the curve, you will see why also the physics are very important. So by the way, this scenario is I'm driving here and some oncoming traffic, postal car, standard cars here. They are detected. You can see it from here by the sensors, sending back information on all of this. And here I have a bus with an accident and an emergency come along. And now what does this truck is doing? It's making a full brake. It's making a full and emergency brake. And here you can see I have built this road with different surfaces. Hopefully you can see it from this Zoom session here. Yeah. This does mean I have different friction elements on the left, on the right side. It's a little bit more slippy on this side. And if the truck makes a full brake, it's spinning around. It was, whoa, quite, we were lucky that nothing happened so far with this bus, the children in there, and also not the emergency car in here. Yeah?
Right.
And this, by the way, as I said, don't underestimate the physics of the truck or the car. If you would not have this taken into account, you were not able to demo such a scenario. Let's quickly change just the road profile. Don't care about this tooling here, it's model desk. I will just change it from wet to dry, okay? Everything keeps the same, just save and download. I do not have to restart anything, just change it during runtime and now rerun the same scenario again, but with a different friction. And now let's wait what's happening now. Yeah, and what would be the differences? As I said, everything keeps the same scenario, the same environmental conditions, only the friction on the road has been changed. And as soon as the AV stack or the AEB functionality is recognizing here, now the bus, it will start braking and it sees, oh, time to collision is quite quick. It will make a full brake again. And here you can see the difference. It's completely changed at the full brake system, but because I changed only the friction of the road. Yeah. And to really validate and get a really broad test coverage, I said under all conditions. You also want to change the environmental conditions regarding the physics of the track here. Yeah. And this is very important that you can also take this into account.
Wow.
Yeah, so this is another demo I have on my laptop here. The other was one on another PC. I'm now driving in a realistic highway scenario. If I start my scenario now with a car, not a truck, other agents, other actors are appearing here. Yeah, and I can now, for example, check my ACC controller. And now another car will come up, this guy here, will bypass me, will come into my lane, and then will make a break. I hate these SUVs coming in and then breaking down. Anyway, I will brake too. And then I will follow this. By the way, follow this roadworks on a highway. And this is typical scenario, at least in Germany, where we have these yellow lines on. And now you can even see this guy is again braking and I have to brake again as well. Yeah, and this is a very important point here that I can also test the AV stack, but also just ACC, so AV ADAS functionality. Right. And what I wanted to show to you here, this is just from the observer view, but you can see the whole scenario from the view of the camera. Let's reset this guy to the beginning. Reset, we'll put it to the beginning and start it again. And you can see now the whole scenario is the same, but through the eyes of the camera. And why is this important? This is so important because now you can do your perception algorithm.
Right,
yeah,
exactly.
And I have also a demo for this. Don't care about this tool. I will just activate my real-time perception algorithm. Here I'm running a YOLO, you only look once, a very famous algorithm, a pre-trained network. And here are the results. This is real-time perception of my camera. Now, during runtime, I mean, just feeding in information from a virtual environment, so from Aurelion. And on the pure Aurelion data, this general YOLO algorithm is working and is giving me the category of the different elements in here. This is a car, this is a truck. And this is exactly how your real AV stack would work. And this is a big challenge. Here we are talking about AI. Yeah, you need neural network that needs to be trained and tested. And this gives you the virtual environment with Aurelion, for example, to come here to our results, to bring everything here into a virtual environment. And here now on the left side, you have exactly the elements that you may remember from my live demo. I had this truck, make a full brake. I have this vehicle spinning around and pardon, the vehicle on the roadworks on the highway. And here, for example, you have a look into the 3D objects. And for example, you could place another sensor here if you need another sensor. And then you have this big field of scenarios. Exactly the scenarios that I drove interactively, you can now do it on scale. Here, for example, is exactly the scenario where the car make a full brake. I just brought it from my single PC into the cloud. Why is this so important? Because, as I said, I can now do it on scale. That means I can do my test campaign, call it scenario-based testing. where I can define different test suites, like the cut in here. And if I click on one of these elements, you can see, wow, I executed more than 1 hour of simulation of execution time, but it just took me 20 minutes because I could scale it up with number 3 because I have 3 execution nodes available. And you could even increase it much more and more, especially the standard scenario ALKS, where you can run, more than 800 runs, 15 hours of real time, of simulated time, execution time, but it just took me 4 hours here. And as a result, this is very common graphics from the results, for example, from an ALKS scenario. This is a typical characteristic in here, where you can see, well, here was a mistake. I had a crash when another car coming into my lane, this guy coming into this lane, and so on. That means you can start with interactive views on your local desktop and later on bring everything into the cloud for a highly scaled execution plan.
And so when you have some of those failures, like you're pointing out here and just above, are you able to drill down into those anymore?
Yes, yeah, you can just click on one item, this one, and here you will deep dive now. All of the data that is needed for reprocessing is stored in a result zip. And you can have an overview about the so-called observer and your KPI definition. Pardon, for some reason it's scaled. And here, for example, you can click on this and see, well, this flag, the collision flag, change it to 1. So there was a collision at this time. This was the impact speed. This was the overall speed here, and so on. So you have additional information available. And now you could even rerun this crash scenario at an interactive part here. We call this interactive simulation, where you have exactly the same conditions as before, but now running it in the cloud. And now you will see it looks like a pure graphic, but this is like the car, the real car is seeing the environment. Everything consists just of lines, lanes, and bounding boxes. And out of this information, your AV stack needs to make the right decisions, the motion planning, and so on. Yeah. That means from a failed test run, I can do an interactive rerun here and check why there was a failure in here and so on. So you can check additional signals here, like the velocities, accelerations. So you have access to a huge amount of data. Here, for example, this guy comes into my lane and there was nearly a crash. Okay, and there, so I can easily, let's say, validate and debug it also directly within Zimfera.
Michael, that's literally amazing. And it opens up a whole lot of potential and also for me, a whole lot of questions, right? Which start at, obviously now you have this really robust simulation environment based on real world physics and it's high fidelity. So you mentioned, look at what your algorithm is seeing. Look at what the perception stack is able to do. Do you have any integrations or are there any plans from DSpace to enable developers to tie their model directly into the simulations that are running so that you can update your model and improve it over time with this massive amount of simulations you could run in Zimfera?
Yes, this is the overall goal. So typically you have to distinguish between what does the customer wants to bring in. We have some customers who would like to bring in parts of their own vehicle model, so from the plant side. But the main goal for sure of our customers is to bring in their control algorithm and to improve it step by step. Like within Zimfera, we have a REST API interface. That means you can easily connect it to your own CI/CD pipeline. Yeah, so typically you're working in, I don't know, ADA, something like this, and you would like to use just Zimfera as a black box, as a quality gate. Just to check if I change something at my SUT, how would this affect on the overall results, passed and failed, between these different scenarios? Yeah. So you can connect it with an ALM tool and others as well because of the openness here.
I'd love to have you back on so that we can go into some more detailed analysis of how an AI is able to evolve over time and then the ways that you're able to use it in different contexts in this virtual world that is basically a mirror image almost exactly of
Yeah.
what you'd find in the physical world.